Good morning, friends. Today we will see chemistry of vitamin B6, which is also known as adenine and pyridoxine. Point number 1, the structure of vitamin B6 is given. Its molecular formula is C8H11NO3, and in the structure you will see the pyridine nucleus is there. Position 2 is with methyl group, position 3 is with OH. Two more CH2OH groups are there at the position 4 and 5. Point number 2, its melting point is 160 degrees centigrade. It is a weak base. Uses, it cures dermatitis. Fourth one, structure was first time coined by scientist Snell et al. In 1942. Common test, it shows the absence of OMe thrice, or sorry, OCH3, that is methoxy group is absent by means of the common test done by more than one scientist. Also it shows the absence of methyl amino group, friends. So all this information we will collect slowly together to reach to the final conclusion of structure of vitamin B6 as structure number 1. Zervitnov test is the name of the scientist, allows us to conclude that there is a presence of 3 active hydrogens, friends. 3 active hydrogens are, see, position number 3 you have OH, one hydrogen is there. 4 you have CH2H, one hydrogen is there in the OH, and one more hydrogen in the next CH2H group. So Zervitnov reaction detects the presence of 3 active hydrogens, friends. Reaction with diazomethane. When you allow vitamin B6 to react with diazomethane, it forms monomethyl derivative, right, which upon further acetic anhydride treatment gives diacetyl derivative. Here there are 3 OH groups, right, and the position number 3 which has got the OH which is phenolic type, right, which undergoes methylated with diazomethane, and then remaining 2 OH which are at the part of CH2H, they undergoes reaction with acetic anhydride, gives you diacetyl derivative, and therefore 3 OH groups present, one is methylated, right, and it may be the phenolic one. How to detect that one? As when you allow vitamin B6 to react with the FeCl3, it gives particular coloration confirming that position 3, right, or you can say one is phenolic OH group, that OH group is directly connected with the aromatic ring structure. Here it is pyridine nucleus, and 2 OH groups are alcoholic OH groups. They are undergoing acetylation. What are these 2 groups? CH2H, CH2H. Point number 8, UV spectra of vitamin B6 close to, and hence it proves the presence of 3 hydroxy pyridine nucleus, friends. Monomethyl ether derivative of pyridoxine, when you allow it to react with lead acetate, no reaction occurs. That means 2 alcoholic OH groups are not on adjacent position. Friend, listen to me. The positions of 2 alcoholic OH group, OH, CH2, then there is one carbon of the ring structure, goes to the one more 5th carbon of the ring structure, then there is a CH2H. So total they are separated, CH2H, CH2OH plus 2 carbons of the ring structure. That means 2 OH are not on adjacent position. How do you confirm? Monomethyl ether of pyridoxine, when it is reacted with lead acetate, no particular reaction occurs. Therefore 2 alcoholic OH groups are on non-adjacent positions. Methyl ether of pyridoxine. How do you prepare monomethyl derivative? By diazomethane, friends. When monomethyl ether derivative of pyridoxine is allowed to react with alkaline KMnO4, it forms methoxypyridine tricarboxylic acid. Molecular formula is given C9H7NO7. And this methoxypyridine tricarboxylic acid, friend, listen to me, it is a oxidation, alkaline oxidation, right? Tricarboxylic acid derivative is obtained when it is allowed to react with FeSO4. It gives blood red color, which is property of pyridine 2 carboxylic acid, friend. Therefore tricarboxylic acid form, right, one of the COH group is at position number 2, right. And friends, if you remember the structure, this is because of oxidation of CH3 group, which it was present at position number 2. And tricarboxylic varies from 2 more COH. They are because of oxidation of CH2H friends. So monomethyl ether of vitamin pyridoxine upon usual alkaline KMNO4 oxidation. Usual alkaline KMNO4 oxidation means you are not controlling the condition. Then what is happening? Anhydride of a dicarboxylic acid is formed with loss of one CO2. The hydrolysis of this product, that is dicarboxylic acid, when you hydrolyze, the anhydride of this dicarboxylic acid gets converted into dicarboxylic acid derivative, because anhydride upon hydrolysis will produce 2COH, for example here. And after hydrolysis, that means carboxylic acid groups are formed. When you allow it to react with FeSO4, no reaction occurs. That means these 2COH groups forming anhydride are on adjacent position, but none of them is at position number 2. Why? If one of these carboxylic acid group is at position number 2, then FeSO4 must have given positive observation, which is not happening. Therefore, usual alkaline KMNO4, you are losing carbon dioxide, right? It is from the position number 2 you have the methyl group which gets converted into COH, and then it is lost because you are employing harsh condition here. And fourth and fifth position you have CH2H. They both will be converted into COH first, and then anhydride is formed. So this anhydride, again methyl ether of vitamin B6 or pyridoxine upon usual alkaline KMNO4 oxidation, anhydride of a dicarboxylic acid is formed with loss of CO2. And this anhydride, when you try to carry out hydrolysis, the product form will not give any reaction with FeSO4. Therefore, 2COH forming anhydride are definitely on adjacent carbon, but none of them is at position number 2 because no coloration with FeSO4. So two possible structures are for methoxy tricarboxylic acid. Two possible structures, they are tricarboxylic acid derivative of vitamin B6 are structure 1 and 2. See, this tricarboxylic acid we have obtained under control condition, first alkaline KMNO4 condition, right? Not second one. So two possible structures are this, and both the structure you see, you will find position 2 with the COH, and that is why it was giving FeSO4 reaction. So these two possible structures of tricarboxylic acids are there. Now the third one, pyridoxine methyl ether. 3 oxygens are there in pyridoxine methyl ether, friends. Pure pyridoxine, vitamin B6, only monomethyl ether derivative. 3 oxygens are there, yes. 1 oxygen as a methoxy group, right? And 2 oxygens are in the alcoholic functional group form. That means they are present in CH2OH, CH2H. So tricarboxylic acid, 2 are from CH2H and 1 from the methyl group which is present at position number 2, right? And therefore pyridoxine, if you compile all this information together, pyridoxine, that is vitamin B6 together, all together, maybe structure 3 or structure 4. See, this is structure number 3 here and this is structure number 4. So still we don't know which one is the pyridoxine, either 3 or 4, friends, right? Now methyl ether of pyridoxine upon oxidation gives a dicarboxylic acid derivative, right? It is oxidation, second oxidation with usual I have written, that means without control, or you can say harsh condition. It gives a dicarboxylic acid, and we have already come across with loss of carbon dioxide, which does not give any coloration with FeSO4. Therefore there is no COH at position number 2, isn't it? So this dicarboxylic acid, which I have marked with the asterisk, this dicarboxylic acid, right, which forms anhydride and phthalate test, that means gives you phthalate test. That means 2 COH groups are in ortho position, right? Then and then it forms anhydride, then and then it gives phthalate test. Therefore the dicarboxylic acid also shows the presence of methyl group, friends. Pure dicarboxylic acid derivative shows the presence of methyl group, and therefore 2 dicarboxylic acids, right, possible are structure number 5 and 6 with the presence of methyl group at position number 2. So 2-dicarboxylic acid with presence of methyl group at position 2 and with the monomethyl ether derivative structure are 5 and 6. Now this 2-dicarboxylic acid structure 5 and 6, Kuhan et al., name of the scientist, have studied anhydride, right? And they found that it was the anhydride of structure number 5 and not structure number 6. Therefore 2CH2OH must be at the position number 4 and 5, right, with methyl group at position number 2, right, and position number 3 it is monomethyl ether derivative. If you remove that methyl ether part, there will be OH. All these evidences, if we put together, the structure of vitamin B6 is structure number 3, and finally it was confirmed by synthesis, friends. So this is the structure of vitamin B6, friends. Thank you. Welcome back, friends. As we have seen that vitamin B6 is the structure proved by various chemical evidences, and finally the synthesis is the proof for the preparation, what you can say, final structure of the vitamin B6. So under preparation or synthesis part, let us try to see some of the methods for the preparation or synthesis of vitamin B6. The first one is Harris and Folker's method, friends. So look at the starting material on the left hand side, where I have tried to draw a curvature line. It is your acetone part. On upper CH2 you have OC2H5, that is ethoxy, and the last carbon which is on the bottom side CH2 of acetone, right, you have the COCH, that is acetyl group. So it is nothing but ethoxy acetyl acetone. Where is acetone part, which I have shown you with the curvature line. The red one is cyanoacetamide. CH3CONH2 is acetamide, but you have the CN group at carbon CH2, that is cyanoacetamide. When these two compounds, two different colors, are condensed together in the pyridine and ethanol, there is a formation of 6-member ring structure. The red part you can see is from cyanoacetamide and the blue is from ethoxyacetyl acetone, just for understanding purpose. This 6-member ring structure, that is structure number 2 on the right hand side of the first line, moving towards the bottom, from that nitric acid allows the nitro group to be produced on position from the methyl side, position 3 with respect to nitrogen, for example. So nitration occurs, which I have written with the dark color, and further treatment with phosphorus pentachloride, the position opposite to methyl group with respect to the nitrogen gets chlorinated, so we are getting blue Cl, right. So this is the structure which we will take further for reduction H2PT in the presence of catalyst. Our NO2 group, which is a third position to say on the methyl side, will get converted into NH2, friends. So this is the structure after reduction. So this structure after reduction we are taking for further treatment with H2 and PDC, that is carbon, palladium carbon, as a catalyst. So the position where you have the cyano group, CN group, right, it will undergo selective reduction to form CH2 NH2. That also I have shown you with the different color. Now here it is HNO2, not nitric acid, HNO2, that we know that NH2 it will get converted into respective OH. Not only that, the CH2NH2 will also get converted into OH when you are allowing it to react with nitrous acid under control condition. Okay, further HBr, when you treat with the HBr, CH2OC2H5 will be converted into CH2Br. Further CH2OH will also converted into CH2Br, friends. And finally, in the presence of aqueous medium, when you allow it to react with sodium silver chloride, both CH2Br will converted into CH2OH, CH2OH, and we are getting vitamin B6, friends. Another method is Harris et al. Method. In this method, first of all, find out alanine. Where is alanine? NH, upper line NH, straight line moving right hand side CH, you have upper side CH3, and that CH is connected to C double bond O. So this C double bond O is COH and this NH is NH2. Then that particular part is alanine, friend. But nitrogen is connected with the CHO, right? That is formyl group. And other side COH is now in the form of ester. Therefore, the starting material with the red structure is N-formyl alanine ester, ester of ethyl ester. When you allow it to react with phosphorus pentoxide in the presence of CHCl3, a 5-member ring structure is formed, which is oxazole ring. Oxygen and nitrogen present as a part of the heterocyclic separated by 1,3 position 5-member ring is oxazole ring, friends. So the position is already mentioned. Oxygen gets 1, 2, nitrogen will 3, carbon with the methyl is 4, and carbon with the OC2H5 is 5. Therefore 5-ethoxy 4-methyl oxazole. This is my intermediate number 1, which I have taken at the bottom. In the last line, the bottom red structure is nothing but intermediate number 1, which we have already synthesized here, and blue color is diethyl maleic, friend. Diethyl ester of maleic acid. Therefore diethyl malate. Now when these two condense together, at the bottom side I am trying to condense this together in the form of cycloaddition reaction. So one is from red reagent, another line is from the blue reagent in the next slide. It undergoes diel-Selder cycloaddition reaction. So the red part of this structure is from oxazole ring, and the blue part is from, you can say, diethyl ester part. The black are the two new bonds are formed as a diel-Selder cycloaddition reaction with a new pi bond between nitrogen and carbon. So this is a kind of bridge structure or intermediate structure, which upon treatment with HCl and ethanol immediately gets converted into pyridine type of the nucleus, where carbon 2 is having CH3, carbon 3 because of acidic condition gets converted into OH, and 2 COOC2H5, COOC2H5 ester groups are still there at position number 4 and 5. Selective reduction with lithium aluminum hydride, both the ester group will be converted into CH2H, CH2H, and finally this is nothing but the structure of vitamin B6, friends. Scientist Snell, we have already pointed out that he was the first to give little idea about the structure of vitamin B6. He was working with vitamin B6 chemistry, and in rats he found that pyridoxine, right, gets converted into pyridoxal and pyridoxamine. Not only that, he says that these pyridoxal and pyridoxamine are the forms which are equal or more reactive than vitamin B6, that is pyridoxine itself. So let us try to see how this compound pyridoxine gets converted into different forms. So first of all, on left hand side top is the structure of pyridoxine, vitamin B6. Now first line, upper line moving towards right, MnO2 in acidic solution or in the presence of KMnO4, the right hand side blue structure is pyridoxal. Friend, what is the difference? One of the CH2H, which it was position 4, has converted into CHO, aldehyde group. Therefore, it is pyridoxal. Further, taking that structure, allowing it to react with hydroxylamine NH2OH, we know that whenever there is a carbonyl group, it immediately reacts with NH2OH, forming oxime type of the structure. So the fourth position at the right hand side, extreme position, CH double bond NOH is the oxime type of derivative of pyridine, what you can say vitamin B6 is formed. And this oxime you further want to get converted in pyridoxal, then allow it to react with nitrous acid, back reaction to giving you pyridoxal, friend. This is the first upper side reaction. Now oxime derivative, which is the right hand side extreme most top corner, when you allow it to react with H2 nickel, friends, so what will happen? There is a CH double bond N, right, OH. This will get converted into corresponding amine. Hydrogens are added, so forming CH2NH at the position number 4, right. So this is nothing but your pyridoxamine, right. This structure is also equally or more reactive than vitamin B6. So H2 nickel gets oxime part converted into CH2 NH2, and this pyridoxamine upper side blue line further you treat with HNO2 friend, you are going to get back your vitamin B6, because NH2, by the treatment of nitrous acid, you can get converted into CH2H, right? Now, from the first structure, that is vitamin B6, if you allow it to react towards bottom side, that is acetic anhydride, both the OH will get converted into anhydride, what you can say, CH2OH derivative, acetyl derivative. And further, when you allow it to react with concentrated ammonia in the presence of methanol, you can get pyridoxamine. And this pyridoxamine, again you can get back vitamin B6, vitamin B6 to pyridoxal, pyridoxal to oxime derivative, oxime to pyridoxamine. So this is how one to another forms are possible. And as Snell tried to study the effect of this particular, what you can say, vitamin in rats metabolism, it is found that pyridoxine, that is vitamin B6, gets converted into pyridoxal and pyridoxamine. These forms are equally or more reactive than vitamin B6. So here this scheme shows how the vitamin B6 gets converted into pyridoxal and pyridoxamine, and again they can be converted back into the original form of pyridoxine, that is vitamin B6. Thank you friends.